Okay, I guess we can go ahead and start the class. A couple of quick announcements before we jump into the lecture. Okay, a couple of quick announcements. First one is for the graduate students. So your midway report on the syllabus, it says your midway report is due next week, next Monday. A lot of groups have reached out to me and have asked for extensions because they couldn't meet the deadline. So what I've decided to do is essentially let you not submit this at all and integrate whatever you have done in your final report, right? If you still want to submit a midway report, you can do so. You will get some bonus points for it. Okay, so if you think you want to get my feedback, you can submit your midway report by that time and you'll get bonus. But you don't have to submit anymore. I will distribute the grade. I will give all of the midway report grade to the final presentation. And keep in mind, for your final, you have to provide a final report and a final presentation. For a student who have registered for the online section of the class, we will use the projector here to do the online presentation. And for the face-to-face students, you have to come to the board. You have to come to class to the online presentation. So that's the first thing. You don't need to submit the midway report if you don't want to. The second one is actually about the exam 2. Exam 2 on the syllabus, I think the exam 2, yeah, it is April 26th, which is the last day. It is a Monday, the last day of classes. Okay. And the week before, Monday 19th, is the graduate presentations. Okay, graduate presentation, whatever. And that Wednesday, which is going to be the 21st, is a wellness holiday. Okay, wellness holiday. I was thinking if everyone, it has to be a unanimous agreement here. If everyone agrees to this, we can move the exam 2 to the, it's going to be to the 19th, and move the graduate presentations to the 21st. Right, then you don't have to come to class on the Monday. So effectively, your wellness holiday, I assume you have other classes as well, but your wellness holiday is going to be, as far as this class is concerned, is going to be on the Monday 26th. Okay, and I mean, in my mind, that would have been a better option for a wellness holiday. Yeah, because that's less not classes. Anyway, so 2 changes: moving the exam to Monday, right, to the previous Monday. And we want to vote on that first. That has to be, it doesn't, that one doesn't have to be unanimous agreement. It just has to be the majority vote. So moving the exam 2 to 19, and then having the graduate presentations on 21st. There are a couple of people who can't do 21st. I will make individual arrangement with them as far as the presentation is concerned. Yes.
So the exam 2, that's not the final exam, is it?
No.
Okay. That's on the 28th, right?
Final exam is on, I think so, yes. I have to double check.
So as it stands, we would have an exam and then 2 days later, another exam.
That's the idea. That's how it is listed on the syllabus. Yeah, you want to avoid that, I assume. I guess, I don't know, I mean, if you want to avoid that or not, but it is better to have the exam on the I'm open to moving the exam even earlier to the earlier part of the semester, but the reason I have it, I'm planning to have it on the last half class is because I want to cover whatever we didn't cover in the first half in the second exam, right? So if you don't mind, like having some parts of the class in the final exam and not covered in any of the midterm exams, then yeah, we can move it to April 1st as far as I'm concerned. Okay. So yeah, this is something you can think about. So let's vote on the first one. Moving the exam from 426 to 419. So
Hands up for yes.
yes, I guess, yeah. So we have a couple of people who are against this. Or you don't have any opinion? Which one is it?
For me, I have a trip plan, like I was saying about leaving on the 21st, so that's my only hesitancy with that. And so
Okay.
I was just trying to figure out like what makes most sense for me.
Okay. Okay. No opinion. Okay. Doesn't matter. So for your case, we can of course like come up with an individual like solution to your problem.
Yeah, I'm fine with anything as long like as we figure it out. Like I guess.
Okay. I assume you don't want to come in for the wellness holiday as well, right?
What? I'm sorry.
So the second thing that we wanted to vote on was to move these graduate presentations instead of 26th to 21st, which is a wellness holiday. I assume you're not going to be here and there because you are going on a trip. Okay. And okay, so this is what's going to happen because the second part has to be unanimous. So 419 exam 2, 426 the graduate presentations. Okay, and this last class may go beyond the 1 hour and 50 minutes mark. We have the 75-minute mark we have for this class. Undergraduates have to sit it for the 75-minute. You have to ask questions if you're an undergrad. If not, if you're a graduate student, I assume you have to sit in for all of it. Okay. Does it make sense? Any questions? No. Okay. So let's begin chapter. I will send out an email about this as well. If you are someone who can't do the exam 2 on 19, please reach out to me. And I know we already have one person who can do this. So we can come up with a solution for your problem. Okay. Today's topic is chapter 4. Yes. Check the messages. Oh, we have 4 messages here. Yes, please, but could we get solutions for the last homework before that? Okay. Yes, I can do the presentation on 26. Yeah. I know about your presentation problem. We'll figure that out. And the homework, you definitely will post all of the homework solutions you need before that. So I will move the homework days a little bit as well to make sure that they are posted before the exam. Okay, so chapter 4. Chapter 4, we are going to mostly focus on thin airfoil theory. Okay, thin airfoil theory is the crown jewel of analytical aerodynamics. That's actually something that people use for the first half of the 20th century to analyze airfoil, to design aircraft, to do a lot of things. And we had actually a lot of progress during that time in aerodynamics. Aerodynamics effectively started in the 20th century and up until the 1950s. This was one of the only tools they had to analyze airflow and design airflow. So it is a very important analysis historically, but it is something we still use today, the idea. And this thin airflow theory, the whole idea, the whole method was developed by the Germans during the World War I, just a little after the World War I, actually. A German scientist. I don't know the name of the German scientist, but it was developed by them. And it is mostly focused on using circulation to find lift coefficient, right? And to find the lift slope, which is something we will talk about. Okay. There are a couple of things we need to understand before talking about thin airflow theory. First one is understanding the relationship between lift coefficient and angle of attack, as well as the drag coefficient and angle of attack, moment coefficient, angle of attack, and lift coefficient and the drag coefficient. So becoming familiar with these graphs and figures that are very popular in aerodynamic analysis, very common in aerodynamic analysis. Then before that, actually, we want to become familiar with the naming scheme of the airfoils that NASA has been using since the earlier part of 20th century. And at the time, it was called NACA. It wasn't called NASA. When they started doing this space exploration, they changed the name to NASA. I mean, they changed the abbreviation completely, but the only thing they changed the words completely. So the naming scheme is the first thing. Then we will move on to the CL versus alpha lift coefficient, all of those things, and then we'll move on to some of the things, prereqs we need for theory, like the Kutta condition. The pronunciation of this word is always a mystery to me. It's the name of the scientist that developed this theory, essentially. A German person. I think the correct pronunciation is Kutta. But we are going to Kutta, something like that. And then we move on to Kelvin circulation theorem. And eventually we will talk about the thin airfoil theory. Okay. So let's talk about the first part first, the naming scheme of different airfoils. There are three very common naming schemes. All of these very common naming schemes start with NACA or NACA. Okay. The first one has only 4 digits, like 2412, which is one of the more popular ones. The second one has 5 digits. As an example of the second one is like 23012 again. And the third one also has 5 digits. There are other naming schemes, and these are a couple of examples. There are other naming schemes that are out there, but these 3 are the more popular ones. But what does these digits stand for? For the first one, the first number stands for the max camber. That's as a percentage of the chord. Of the chord. Okay. So that's the first number, this number. Okay. So NACA 2412, first number tells you that the max camber is 2% of the chord length. But what is the max camber? Have we talked about this? I don't remember. No. Okay. So to understand what the max camber is, we have to talk about an airfoil. Hopefully, at this point, we already know what an airfoil is, right? So it's a 2-dimensional cross-section of a wing that is parallel to the flow, right? That's the definition of an airfoil. Let's say you have flow coming in with V infinity. The shortest distance between the leading edge and the trailing edge is called the chord. the line that has the same distance from the top and the bottom of the airfoil. The top is called the mean camber line. So mean camber line has the same distance from the top, the upper surface and the lower surface of the airfoil. Okay. And this is also the course, the shortest distance between the leading edge and the trailing edge. Okay. And the distance between these two is called the camber. So first digit here is telling us the max camber as a percentage of the chord. So max camber, the maximum of this distance between the mean camber line and the chord line is going to be 2% of this length, whatever this length is, right? The shortest distance between the two, the leading edge and the trailing edge. Okay. And the second digit here, I think everything else we have already talked about. Let me just make sure. Yeah. And the thickness of the airfoil is, of course, the distance between the two. The second digit here is the distance of this max camber from, or the location from the leading edge. Let's say distance of this max camber from the leading edge. So where does this 2% happen? Okay. Let's say here you have number 4. And that's a percentage multiplied by 4. So this location of this max camber is 40% of the chord, based on what you see here. So the max camber on this specific one happens roughly at this location. Okay, 40% of the chord length. Okay. Any questions so far? Just the naming scheme. The third one is going to be maximum thickness. Again, as a percentage of the chord. So the maximum thickness of this airfoil is 12% of the chord, which essentially means that your airfoil is a fairly thin airfoil. I mean, okay. Any questions about this?
Is the second number 40%?
4 multiplied by 10%.
Okay.
So essentially, yeah. Or you can say that you have to divide this number by 10 to get the location of, and multiply by the chord length to get the location of max camber. Okay. So this is for the first generation. This numbering scheme belongs to the first generation of the airfoils that were designed by NASA at the time. NAC. The second family of airfoil with the 5 numbers. So we have 5 numbers now. 2 here, or the first digit number, is your lift coefficient multiplied by 3 by 2. That's the design lift coefficient. Okay. Or what I mean is you have to multiply this number, whatever this digit is, by 3 by 2 to get the design lift coefficient, and divide it by 10. So what is the design lift coefficient for this airfoil? It's 0.3. I'm sure they had the reasons when they were coming up with this numbering scheme at the time. It's going to get weirder, actually. So this 30 here, the number 30, is, yes. The first digit, whatever that first digit is You have to divide it by, multiply it by 3 by 2, and then divide it by 10 to give you the design lift coefficient. Then 0.6 would be, yeah, your design lift coefficient. Okay? Same, yeah. Okay. So if you are all clear on the first number, the second number is actually, which is 30, second two numbers, is twice the location of max camber as a percentage of the chord length. So for this specific airfoil, the location of max camber is 15% of the chord length. So to find the location of max camber, you have to multiply it by half, then divide it by 2, then divide by 100, then divided by your chord length, whatever that is. So this one is 0.15 of the chord length. Okay? And the third set of numbers here is again your maximum thickness as the percentage of the chord. So the same as before. The maximum thickness is 12% of the chord. Okay? Yes.
Are these like for this one? Is it like set, or does it also depend on like the variables in the 5? Like, does it vary? Is it ever going to be like 1 over x times 1 over 3 times 100?
No.
Always do that.
If you are dealing with this generation of airfoils with like 5 numbers as a representation of that specific airfoil, this is how you find the specifics of the airfoil. Okay. And for the third one that we want to become familiar with, the first number is the airfoil series. So it doesn't really signify any specific design parameter. The series themselves signify design parameters. But the third number is the airfoil series, the first number. So the series of this airfoil is the 6th series of this generation. The second number is the location of minimum pressure from the leading edge, the distance from the location of that from the leading edge, right? Divided by 10 as a percentage of from as a percentage of chord from leading edge divided by, you have to divide by 10 actually first. So minimum pressure on the top surface for this one happens at 0.5 chord length, right? So on an airfoil, let's say this is your airfoil. Minimum for this airfoil, minimum pressure happens here. Does this make sense? And the third number is your design lift coefficient. Design CL divided by 10. So you have that your design lift coefficient here is going to be 0.2.
It's not multiplied by 3 halves again.
Not anymore. Yeah. And the fourth, this is the last two numbers are again max thickness as a percentage of the chord length. Okay. Airfoil numbering schemes. Most of you, for your analysis, if you're a graduate student and you're working on a project, if you have to choose a wing type, you are probably going to choose one of these earlier generations, like 2412 or Yes.
This says max what?
Which one? Max thickness. This one? Yeah, max thickness. Most of you are going to use one of the earlier generation of airfoils, which means this 4-digit series. NACA 2412 is one of the most common airfoils in consumer aircraft. So in lighter aircraft that you can just go and buy, right? They're pretty expensive though.
What's the last 2 digits on the 5 digits?
The last 2 digits on all of them is the maximum thickness.
Okay.
On all of them as a percentage of the core. Okay. So, any questions? Yes. There are a lot of there are like millions of reasons about it, but it is the simplest to manufacture. Right? You can see the shape of it. That's the first thing. And it's being worked on for like 100 years now, right? Close to 100 years now. So people, the designers know everything about this airfoil, the lift coefficient, how it's going to perform during the flight, all of those things, right? And if you want to put it on a Cessna aircraft, which is a I don't know how I don't know what to call. I don't know what to call the Cessna aircraft, but it is essentially a very light aircraft, 2-seated aircraft that you can like have 60 hours of training and you can start flying it, right? We actually have one of our students who can fly a Cessna. It's very simple. You have seen. I'm 100% sure you have seen a Cessna. So this is what they use on the like cheapest Cessnas, right? Does this make sense? Okay. Yeah. Okay. If there's no other questions, let's move on to the second topic of today's class. Is the most important plot you are going to see in aerodynamics, or most common, which is lift coefficient versus angle of attack. In general, this plot starts from somewhere here. So lift 0 can be obtained at the negative angle of attack. Okay? And it goes to a maximum. Then you'll get to see a very sharp decrease in the lift direction. Then you will see an increase. So let's talk about different regions of this figure. This part is called the zero lift angle of attack. Okay? This essentially signifies the angle of attack at which your lift is going to be 0. Okay? How does that happen? How can your lift become 0? Think about it. What does lift depend on? Exactly. So if you have an airfoil, if the pressure distribution on the bottom and the top is equal, then lift was pressure on the bottom, pressure on the lower surface minus pressure on the upper surface. So these two are equal. Okay? But the question is, why do we get a negative angle of attack? For most airfoils, actually, for this condition to happen. Right? Why the angle of attack is negative? Yeah, but okay, that's correct. That's definitely a correct answer. So we usually design an airfoil so it can fly or generate lift at 0 angle of attack. How do we do that? With introducing camber. So when you introduce something like this, a camber, what's going to happen is that you are going to have higher pressure on the bottom or on the lower surface of the airfoil anyways, because of that camber, right? In regular, let's say you are dealing with a flat plate. If you have an angle of attack, whatever angle of attack, you are pushing this plate in this direction, right? Any angle of attack. So you're definitely going to get some lift and some drag, that's for sure. But if you have the flat plate parallel to the flow, which essentially means that your angle of attack is zero, then you are only pushing it in this direction, right? The same is true with the cylinder. We have talked about the non-lifting cylinder, yeah? The pressure on the bottom and the top are similar. So if you create a cambered airfoil like this, in 0 angle of attack, you will get some flow here that are going to push the back of the airfoil, right? Upwards, which essentially means that you will definitely get some lift. You'll definitely get higher pressure on the bottom compared to the top. So, if there's a situation that you want to get 0 lift, you essentially have to make sure your flow is coming at your airfoil at the negative angle of attack. So your airfoil is tilted this way, not this way, right? If you are dealing with a cambered airfoil. But the question I have for you is that what do you think will happen to the 0 lift angle of attack if you are dealing with a symmetric airfoil? What would be the angle of attack at which a symmetric airfoil will give you 0 lift? Think about it. The reason we have lift generation at 0 angle of attack is because of the camber. If you remove that camber, meaning that you are going to have a symmetric airfoil, how much lift would you generate at that 0 angle of attack? None, right? Because the pressure distribution on the bottom and the top theoretically will be the same, right? Okay. So if we were dealing with a symmetric airfoil, the CL versus alpha would have looked like this. It started from 0. The 0 angle of attack for a symmetric airfoil, the 0 lift angle of attack for a symmetric airfoil is going to be 0. So that's the first part of this figure that you need to understand, the 0 lift angle of attack. Then we are going to focus on this region. Or let me use another color. This is actually the region which we are going to analyze in this class. This is the region where we can safely assume that the lift or lift coefficient increases linearly with angle of attack. And we're going to prove this later in today's lecture. Okay, we're going to see that later in today's lecture. So this will be the topic of this chapter in general, this region. Well, what is going to happen if you increase the angle of attack enough or more than what you're supposed to do? You are going to get to a lift, you are going to see a maximum generation of lift, and afterwards, you're going to see a sharp decrease in the lift generation. So essentially what this means is that I'm increasing the angle of attack. At some point, my lift generation is going to decrease, right? My lift is going to decrease. This is called the stall condition. So a stall condition is a condition at which you are going to see a huge drop in the lift. Okay. On this figure, a stall condition happens when you increase the angle of attack enough or more than enough. Okay? If you go behind the Libby. But the question I have for you is that what is the mechanism of the stall condition? Why, or what is the mechanism of the lift drop at the stall condition? Or why does the lift decreases after or during the stall condition? Does the question make sense? Do you understand the question? Okay. So let's talk about it. What do you think is happening there? I assume you understand, hopefully, you understand that why, let's say we are dealing with a symmetric airfoil. If you increase the angle of attack a little bit, you will get some component of force in the normal direction, which means that you are going to have lift generation, right? That's the idea. If you increase the angle of attack, you're going to get a bigger component of force that is being exerted on your body in the lift direction, which means that you are increasing the lift, right? But at some point, this increase in the angle of attack is going to be harmful to us. What happens? What is the condition that triggers the stall condition? Yes?
Is there like too high of a generation of drag because there's more like surface area coming in the direction of velocity?
No, but okay. That's not the main mechanism. I mean, the generation they are coupled to each other, but that's not the reason you have a drop in lift.
Is the lift sorry.
Doesn't matter. Any of you can go ahead. He had his hand up first, so.
Since it's like a component, since as one goes up, the other goes down, so like it's too high of an angle, then there's more going forward. It's not like generating lift in the y direction, it's just pushing it in that.
No, that actually it should be the other way around, right? If you are increasing the angle, your lift should go up. Okay. If you increase, that's after the stall condition. So there is something happening to the flow that causes this drop. And the reason is not necessarily, it is the increase in angle of attack, but it's not the component of force in that direction, right? Okay. Anyone else? Any ideas? Yes. Oh, he wanted to say something. I am sorry.
I was just gonna say, kind of a guess, but like, does the flow velocity change over the top versus the bottom?
The flow changes. The flow velocity will definitely change when you're
Does
flush.
the pressure start to like increase over the top versus the bottom?
Okay, the pressure starts to increase over the top. Okay, you are moving in the correct direction, but what happens? What triggers that increase in pressure? Or what increases the change in the flow field? What triggers the change in the flow field?
The angle of attack?
The angle, no, not the angle, not necessarily. It is the angle of attack, but the mechanism is not just the angle of attack. Exactly. So that's it. That's the answer. That's the answer we are looking for. Flow separation. And the flow separation happens because of the viscous effects. So, but what is the mechanism? What does it mean? The idea is when you have an airfoil and flow is passing over it, you're going to get some boundary layer formation, right? In which your velocity goes from, if you have no slip condition, your velocity goes to 0 to some value. Okay? When you increase the angle of attack, what's going to happen? What do you think is going to happen to this boundary layer? It's going to become more dominant, right? The thickness is going to increase and increase and increase. And at some point, let me your boundary layer is going to be this. You see the thickness at the back is going to be very high, the boundary layer thickness. And this is a region when you have a very huge velocity gradient, 0 from whatever. At some point, you will have what's called an adverse pressure gradient, right? So the pressure gradient, you have higher pressure here, lower pressure here, so your flow is moving in this direction, right? But at some point, your pressure gradient on the flow will be in this direction, will be positive in this direction. So it means that the flow is going to is being pushed back on the airfoil, right? Does this make sense? So flow is going to in this direction, then you will get adverse pressure gradient. Some parts of the flow here is going to be pushed back, right? So you're going to see vortices generation. The generation of vortices, circulation. You will see not the circulation, you will see the flow circulating on top of the airfoil, right? That is called, essentially, when that happens, we say the flow has separated. The original flow doesn't really act here anymore because your air particles are moving in the other direction. Right? And we are going to have an adverse pressure gradient here. This adverse pressure gradient is going to decrease your the pressure difference between the bottom and top of the airfoil, right? Because we have a high pressure region on top of the airfoil at the end, right? At the end of so pressure difference between this side and this side is going to decrease. That's why you see a sudden drop in the lift. Is this clear? So the stall condition. That's what we call a stall condition, and you want to avoid that, right? Because you are going to put in more energy. You're going to burn more fuel and get lower lift, right? You don't want to have that. But as you can see, after the stall condition, the lift generation will pick back up. So after a small dip, we will see an increase in lift again. Why does this part happen? Hopefully by this point we understand the flow separation. As we increase, your flow is going to separate from the back of the airfoil, back of the wing, right? And that's when we see this dip, a continuous dip in lift, right? But if you increase the angle of attack enough, what is going to happen is that your lift is going to go up again. What do you think the mechanism behind this is? Hopefully we are clear on what the question is, okay? Think about it. What do you think will happen when you increase this angle of attack? Some parts of the flow has already separated. If you keep increasing the angle of attack, what is going to happen is that you are going to get this region in which the flow is, you have like flow circulating around itself. And the original free stream is bypassing this region. What do you think will happen if I increase the angle of attack even a little further?
Say the magnitude of the vorticity region on top would decrease, then that would lessen its effects on the total lift coefficient. So then the amount of pressure on the bottom of the airflow would just keep going up.
Okay.
The top now has less percentage of the air going over.
You're moving in the right direction. Thank you. And essentially what happens is something we call vortex shedding. So the airfoil sheds the vortex. So this vortex region is going to leave, right, as you increase the angle of attack. And you will have a small region, a small window of flow reattaching the airfoil. That's where you're going to see this increase. But then we will get the flow separation again, and this cycle continues, right? That's why we are not really interested in what happens after the original stall condition. So vortex shedding. So these are the things that may show up in your descriptive problem. What is vortex shedding? And this is something you have to have in your vortex shedding. Will trigger another mechanism called the flow reattachment. But actually, the explanation of why we are going to see a decrease in lift coefficient, and then why does the lift increase after a while, after the stall condition again, is something that will probably show up in an exam, in one of the exams, either the final or the exam 2. Okay. So we understand all of the different regions of CL versus alpha. Well, as I said, we are only interested in the region where your lift coefficient is increasing with angle of attack, which is a linear region. We are going to assume it's a fairly good assumption. We're going to assume that this is a linear region. So let's say this is your alpha. This is your, let me actually move it back here. This is your CL. Our CL is going to change like this. This is the only region we are interested in. At the same time, your aerodynamic moment is going to around the quarter chord is going to change like this. So the pink one is aerodynamic moment around the quarter chord, and your drag coefficient is going to act like this. This doesn't mean that the drag is going to be less than lift. It's just notice the trend. Okay, so with the increasing angle of attack, your drag coefficient is going to increase as well. I mean, that there is an optimal value, but that's a whole different discussion that we are not going to have. We are mostly focused on lift in this chapter, or in most chapters in this course. Okay. Here, I need to introduce a new concept called the aerodynamic center. If you recall, we defined the center of pressure. It was a question on your exam as well. So I'm going to ask you again, what is the center of pressure? Anyone?
So all the moments are equal to 0, right?
Moments cancel each other out. So eventually your total moment is going to be 0. Exactly. Aerodynamic center is essentially, I don't want to say the same concept, but essentially is going to serve the same purpose, right? Aerodynamic center is a location at which moments are independent of angle of attack. So if you increase the angle of attack, you are going to get a straight line like this. So these are the moments around the quarter chord. But if we were to use, for this plot, if we were to use the center of pressure, your moments should have been 0, right? But the location of the center of pressure would change by increasing the angle of attack, right? It is possible for it to change, right? But the location of aerodynamic center, based on definition, the definition of it is something that is independent of angle of attack. That's how we find it, right? We make sure that that's a location that is independent of it. So in our analysis, aerodynamic center fits our purpose better because the change in angle of attack is a very important part of the analysis in an aerodynamic analysis. Okay? So, guess we are ready to jump into the theory a little bit. And then we will, we have one more thing that we need to discuss before jumping to the theory. And that is the vortex sheets. Okay. Vortex sheets. If you recall, in chapter 3, at the end of chapter 3, we talked about the source panel method. And we introduced this idea of line sources, right? Right? And we said if you put a lot of line sources beside each other, you're going to get a source sheet, right? That was the definition, source sheet. Okay, so based on this definition for the source flow, what do you think a vortex sheet is? Any ideas? We defined the line sources that were essentially a source flow on a line, right? And then if we said if you put a lot of millions of these lines beside each other, you're going to get a source sheet. So based on this definition, what is a vortex sheet?
A bunch of vortexes next to each other.
That's it. So essentially, instead of line sources, we are going to call them vortex filaments. Which are vortexes that go from negative infinity to infinity, for example. And then if you put a bunch of them beside each other, you are going to get something that is called a source sheet, okay? A vortex sheet. Sorry. So let's have a side view to this source to vortex sheet. Let's say this is your vortex sheet, not the source, vortex sheet. And I want to find the velocity induced at this point P by this vortex sheet, by this section of this vortex sheet. How did we do this when it came to the source sheet analysis? Right? We did do this, right? We found the velocity induced by a source sheet at a point outside of that source, right? So this time we want to do this for a vortex sheet. If you recall from the, I guess, chapter 2 or 3 analysis, or let me ask you, what was the velocity potential of a vortex flow? Who remembers this? Velocity potential of a vortex flow.
Negative circulation over 2 pi times theta.
Exactly. Negative circulation over 2 pi times theta. So this time, this length is ds, and the circulation of each vortex here is a small gamma of s. The velocity induced by this velocity potential induced by this section of the vortex sheet at this point P is going to be d phi, right? Because that's the velocity induced by the ds of this vortex sheet. So a small element is going to be equal to negative gamma of s ds. So the strength of each vortex filament over the span of this small length, gamma multiplied by that length, divided by 2 pi theta. Okay? This is going to be your theta. Okay, so based on this, we can, and the definition of the velocity potential and its relation to the velocity, we can easily find the velocity induced at that location P, to be gamma ds divided by 2 pi r. So this is the velocity induced. Let me write it down. Velocity induced by a small section of this vortex sheet on P, on point P. This is something we have seen for the source panel method as well, where this is the analysis. The idea over there, instead of having a sheet, was that we had a couple of separate panels, right? So that was a little simpler, if you will. I mean, eventually at the end, the analysis was harder because it would have taken you a lot more time. But the idea was a simpler idea. And over there, it gave us a non-lifting flow. So let's say we have the velocity induced by this vortex sheet. What I want to measure, or what I want to find next, is the velocity jump. You have a question? No? I thought you had her hands up. That's right. What I want to find next is the velocity jump from here to here. Okay? How much velocity is going to change between the upper surface of this vortex sheet and the lower surface of this vortex sheet, right? Because if there is no velocity difference, we are essentially, our analysis is going to be useless, right? But if the velocity is going to be the same, it essentially means that the pressure is going to be the same, and it will be a non-lifting whatever. So it's not going to help us find lift, right? So let's bring this vortex sheet here. Let's put it inside the box, a small box. I'm going to call this length dn. And I'm going to call this length ds. So think of this as a magnification of this small element. Okay. Let's find the circulation for this. Negative gamma vs ds. That's the integral. But here we only have, let's call it u1, u2, u in one direction, u in the other direction, and this one, v2, v1. Since the velocity is only in one direction, and all of these are in the same direction as your coordinate system, this will be a very simple negative. We're going to move from here to here, negative u2 ds minus negative v2 dn, negative v1 ds, negative or positive v2 the end because of the directionality of it. Yeah, okay. We understand how to get from here to here, right? Just simple lines, one-dimensional velocities is going to result to that. And we want to find the jumping velocity between these two locations, the upper and lower surface of your whatever. So we're going to make this distance smaller and smaller and smaller, effectively eliminate, we are going to eliminate these dn's, which essentially means that we are going to look at one very small section of this vortex sheet for which the circulation is going to be a small gamma, the function of s, small gamma ds, and that's the idea. If you eliminate those velocities, you're going to get u1 minus u2 multiplied by ds, which essentially means that we are proving the velocity jump is present, is there, and is equal to the circulation of that part of the vortex sheet. Okay, so this type of analysis can be helpful to us in finding the analytical lift. Okay, if we replace the airfoil with a vortex sheet. Okay, so flow over an airfoil, a very complicated type of flow. If we replace it with a vortex sheet, it is possible for us to find lift. And that's the backbone of thin airfoil theory, right? We want to replace the airfoil with a vortex sheet. Let's talk about two theorems that are very important in this analysis. I just mentioned them in the beginning of the class. The first one is the Kutta condition, or Kutta condition, however you want to pronounce it, is fine. And then we will talk about the Kelvin circulation theorem afterwards. The Kutta condition tells us the value of circulation over an airfoil is going to be a value that ensures the flow leaves the airfoil smoothly. Okay? You have this airfoil. The idea is if the flow does not leave the airfoil smoothly, you are going to get a huge velocity gradient here. You may actually, at the beginning of the flow, this is what happens. You're going to get a huge vortex flow here, and it's going to mess things up. But the idea of the Kutta condition is that the nature chooses the circulation in a way, after you have reached the steady state conditions, that the flow leaves the airfoil smoothly. What does it mean? It effectively means that your streamlines, if there is no flow separation, of course, are going to look like this. Okay, so what does this mean for the velocity at the trailing edge? Velocity at the trailing edge. In general, we have two types of trailing edges. One is this type of trailing edge. Let's say this is your airfoil, which is called the finite angle trailing edge. And the other one is called a cusp trailing edge. That looks like this. CUSP, cusp trailing edge. So for your flow to leave the airfoil smoothly, for this condition, let's think about it. Let's actually talk about it. We should need to talk about it. Just before the trailing edge, your velocity is in this direction. That's the velocity on the top surface. And just before the trailing edge, your velocity on the lower surface is v2, right? They are in the different directions, right? So what does it mean? There are two flows in different directions that are going to meet each other at one point. Does this tell you that the flow is going to leave the surface smoothly or not? No. Why not? Because there are two flows in the opposite direction. There is no smoothness about this, right? So what should be the velocity here then? What do you think we should have the velocity at this trailing edge point? 0, exactly. So because the direction is nothing we can choose, or the nature can choose. They are going to be tangent to the surface, right? So for the smooth condition to happen, for the finite angle, V1 has to be equal to V2 equals to 0. What can Fitz say? Yes. But they will have a component in the other direction as well, right? They will meet each other, and they will, like, you will see a component in this direction. There are two streamlines coming at each other with momentum, right? What's going to happen after they meet each other? The momentum doesn't fade away, right? Okay. So what about this cost condition? It's for the cost condition, you have an infinite angle, which effectively means that the two flows are in the same direction, right? So what should happen at the trailing edge for these two velocity vectors to leave the flow, for the flow to leave the airfoil smoothly? What do you think should happen there? The other time, they had to be 0 because they were in the other direction, in two different directions. This time, they are in the same direction, and we wanted to leave the airfoil smoothly. What do you think should happen here? They have to be equal to each other, exactly. Okay, so this is the Kutta condition. The idea is nature chooses your circulation in a way that makes sure this happens. For a final angle, you're going to get 0 velocity at the trailing edge. For the cusp, you're going to get equal velocity. So what does it mean when we are looking at it as a vortex sheet? What does it mean for the vortex at the trailing edge, for the strength of the vortex, circulation at the trailing edge? What does it mean? Look at the formula we came up with, right? The velocities at the trailing edge are either 0 or they are equal. What does it mean for the circulation at that trailing edge? 0, exactly. So the Kutta condition tells us the circulation at the trailing edge must be 0. That's one condition. Okay? Then we actually have to determine the value of circulation, because the Kutta condition only tells us that the nature will determine the circulation in a way that the condition is met, right? But it doesn't tell us how we should find that circulation. That's where Kelvin's circulation theorem comes into play. The idea of the Kelvin circulation theorem is that the circulation, there is conservation of circulation, if you will. That's what I'm saying. But what the Kelvin's theorem says is that the material derivative of circulation with respect to time is 0. Okay? This essentially means that we can find the circulation needed to meet the Kutta condition, the Kutta condition. Okay. And if you recall, I said when you start the engine of an aircraft, when you start moving, what you are going to get is that a huge vortex generation when you haven't reached the steady state condition yet. You're going to get a huge vortex generation at the end of an airfoil, right? Which will eventually leave the airfoil, leave the wing, and the color condition will be met, right? Eventually, when you reach the steady state. But based on this, the circulation of that, let's say this is a control volume at the beginning, and you have this huge circulation at the end at times t0. And then at time t equals to t1, the circulation has left the airfoil, but it hasn't faded away. It doesn't just go away. Based on this theory, we can, if we divide this, and at time t1, there is no circulation here. The circulation to ensure a smooth flow over an airfoil has to be equal to the initial circulation at the end of the airfoil, right? Because this tells us circulation is conserved. So the whole circulation for this red field has to be equal to 0, right? Because the circulation initially, before the start of the engines, was 0, right? Which essentially means that gamma 1, gamma over the airfoil during flight, has to be equal to negative the initial gamma, right? The initial circulation. Okay. Okay, so the next thing we can actually, with this knowledge, we can start the discussion on the thin airfoil theory. I wanted to finish this today, but I guess we have had enough material. And we are at the end of the class, so I don't think we are going to start the discussing something that we cannot finish. Okay, so before we leave, let's make sure we are all clear and on the same page as far as the exam date is. The exam 2 is going to be on April 19th, right? If you cannot make it to the exam, then reach out to me. We'll come up with a solution for your case, right? In general, it is better for you to make it to the exam because, for example, especially if you want to do it earlier, right? Because like during an exam, I may give an extension to the students, to all of the students. I may drop a question. These things may happen, right, depending on how people are performing on the exam. But if you're doing it individually, I can't extend the same offers because I don't know what is going to happen in the future, right, for everyone else. So it is better to make it to the exam in general. But yeah, we'll make sure it is working. It is fair to everyone, right? It is fair to you as well if you have to take the exam. And then the graduate presentations are going to be on April 26th. Everyone has to come to that class. You have to ask questions. That will be your attendance check for the last exam. So if you don't come in and don't ask questions as an undergrad question, you will lose the attendance point for that class, that specific class. And I guess that's it. Is there any questions? No. Okay. So see you on Monday.
That was a great one.